In this video, I want to look at number 3 on the 2019 AP Statistics test, which is about simple and conditional probabilities using two-way tables. I found something very similar on Khan Academy, so let's start there for practice. We've got 100 students surveyed on which superpower they'd most like to have. Here we've got the two-way table. We've got males and females and total number of students. And then we've got the 3 different superpowers and the total. Sorry, there's a total of superpowers, here's the total students. So let's find the probability that a student chose to fly as their superpower. The probability of fly is this row entry here, 38 out of 100 total. 38 divided by 100 is 0.38. Next, the probability that the student was male. Males are in this column here. We've got a total of 48 out of 100 males, so if we chose one at random, we'd have a 0.48 chance of choosing male. The probability that the student was male, given that the student chose to fly as their superpower. And so probability of male given fly is the intersection of male and fly divided by the probability of fly. Now, I'm not going to calculate their probabilities because of the way the Khan Academy has structured their input field here. So we've got the intersection of male and fly. I'm just going to enter the integer value here. Male and fly, we've got fly here, male here, so our intersection is this cell, 26, and then out of all fly is 38. So we've got 26 over 38. It's going to be our answer. That's correct. And find the probability that the student chose to fly given the student was a male. So again, we've got same thing. We're going to have the intersection of fly and male divided by the second one, which is all males. So the intersection of fly and male is 26 again, but this time we're taking all males, which is 48. 26 over 48. Is the statement about conditional probability true or false? In general, P A given B is equal to P B given A. Well, we just saw that here. We switched these orders, male fly, fly male, and we see here from our experimental statistics that this is not true. They're not equal. 26 over 38 is not equal to 26 over 48. So that is false. And finally, let I represent the event where the student chose invisibility as their superpower, and F represent the event where the student was female. Interpret the meaning of PI given F. So this is the probability that a student chose invisibility given that they were female, meaning that among all females, 0.62 or 62% chose invisibility. So 62% of females chose invisibility, or about 62% of people who chose invisibility were female. And that's that one there. Okay, let's go on to the AP test. A medical researcher surveyed a large group of men and women about whether they take their medicine as prescribed. The responses were categorized as never, sometimes, or always. The relative frequency of each category is shown in the table. Here we've got that same two-way table. In this case, we've got the probabilities, whereas in the Khan Academy example, we had the integer numbers of participants in the survey, I suppose it would have been. It's basically the same thing. We're going to take table values and calculate probabilities using those. What's the probability that the person selected will be someone whose response is never and who is a woman? So we're looking for the intersection in this case. When we see that word and who is a woman, we're looking for the intersection of never and woman. And so we've got never in this column, woman in this row. So our intersection there is 0.0636. What's the probability that a person selected will be someone whose response is never or who is a woman? Well, since we have or here, in this case we had and, which is the intersection. Here we have or, which is going to be both, basically, right? So either or, right? So we've got either they chose never, which includes men, or they were a woman, which includes sometimes and always. And so we're going to take the total number of nevers, which is 0.12, and we're going to add to that the total number of females, which is 0.53, and then we have to subtract from that. Remember, 0.12 is 0.0564 plus 0.0636, and this 0.53 includes each of these three values from that row. So we don't want to count this one twice. If we've added it here and added it here, then we've double added that. So we need to subtract 0.0636, and so we've got 0.65 minus 0.0636. Take out our calculator for that one. 0.65 minus 0.0636 equals 0.5864. 5864. And we could have also added up these two plus this one, and we would get that same value, 0.5864. What's the probability that a person selected will be someone whose response is never given that? So we've got three different types of statements here. We've got the and, we've got the or, we've got given that. And so if we're going to look at given this, given that, then we want to look at first one is never given that the person is a woman, and so that's going to equal the intersection of never and woman, which we already found is 0.0636, and we're going to divide that by the probability that that person is a woman, which is this cell value here. So we've got 53 out of 100, or 0.53, I suppose. It doesn't have to be 100. 0.53 of respondents are female, so again, calculator, 0.0636 divided by 0.53, that is 0.12. So that is the probability that a person chose never given that they're a woman. So 12% of women chose never, or never take their medicine as prescribed. B, for the people surveyed, are the events of being a person whose response is never and being a woman independent. Now remember, they are independent if and only if the probability of their intersection is equal to the product of their individual probabilities. So if and only if P of any event A intersection B, in this case it's never intersection woman, is equal to the probability of never times the probability of woman. And so remember that the intersection of never and women is 0.0636. The probability of never is including men, 0.12, and the probability of woman is including sometimes and always. And so then if this cell times this cell equals this cell, then they are independent. We basically calculated that same thing in the previous example, but let's go through calculator. I've got 0.12 times 0.53 is 0.0636. 0.0636, which is in fact this number here, so yes is our answer. Okay, and moving along to letter C. Assume that in a large population the probability that a person will always take their medicine as prescribed is 0.54. If 5 people are selected at random from the population, what is the probability that at least 4 of the people selected will always take their medicine as prescribed? I'm going to treat this like it's a Bernoulli trial, like each random choice of a person from the population has some percent chance of success, which is always, and some percent chance of failure, which is anything other than always or not always, which in this case includes never and sometimes. And so the probability of success is 0.54. Since we know that, let's set up our Bernoulli equation here. So remember, we've got the combination of our choices from the n population. We're going to multiply that by the probability of success raised to the number of successes we're looking for, times the probability of failure, which is 1 minus the probability of success. And then we've got the number of successes subtracted from the total population that we're looking for. That's each individual trial. In this case, we're going to set up a binomial string, right, because we've got this language here at least. So we need to figure out 4 out of 5. 4 out of 5. And also for 5 out of 5. So here's our probability of success. 0.54 raised to the number of successes we're expecting or looking for, which is 4. 1 minus 0.54 is 0.46. Raised to the number of failures which we're looking for, which is 1, and we're going to round that, and we get 0.19557. And then we've got to also take into consideration the possibility that it's at least 4, but it could then be 5. So we'll take 5, choose 5. Right? And so we've got same basic setup here, except we've got 5 successes and 0 failures. And of course we could cross that one out. And that is roughly equal to a much smaller probability, 0.04592. We'll add these together and we get 0.24149. Okay, so this was actually a fairly simple problem, as long as you remember your conditional probabilities from your simple probabilities and just recognize a Bernoulli trial or binomial distribution when you see one.